Right now, time is moving forward. You know this without thinking about it. The coffee is cooling, not heating. The egg you dropped this morning is broken on the floor, not reforming and leaping back into your hand. You remember yesterday, but not tomorrow. You are getting older, not younger. Time has a direction, a clear, undeniable, absolute direction. And here is the extraordinary thing. The fundamental laws of physics, every equation we have ever written down that successfully describes how the universe works, are almost perfectly symmetric in time. Run the equations forward, and they describe reality. Run them backward, and they describe an equally valid reality, Newton's laws. Maxwell's electromagnetism, quantum mechanics, general relativity, even the standard model of particle physics. All of them work equally well in both directions. None of them single out a preferred direction for time. None of them say that time must flow forward. None of them explain why you are reading this sentence now rather than having already read it and now forgetting it and now unreading it as you travel back into the past. So where does the arrow of time come from? Why does the universe have a past and a future when its own laws seem indifferent to the distinction? This is the problem of the arrow of time, and it is one of the deepest unsolved questions in all of physics. Not unsolved because we haven't thought hard enough. Unsolved because the more carefully you think about it, the stranger and more profound it becomes. This video is going to take you all the way through it, every major answer, every open question, every place where physics currently runs out of road. We're going to start from the very beginning, what time actually is, and build to the frontier where physicists are actively arguing right now. No comfortable shortcuts. Let us begin with the thing most people think explains the arrow of time. Entropy, the second law of thermodynamics. You have almost certainly encountered this idea before. Entropy is disorder. The second law says entropy always increases, disorder always grows. Things fall apart, eggs break, coffee cools, rooms become messy. And since entropy only increases in one direction toward greater disorder, it gives time its arrow. Past is low entropy. Future is high entropy. That is why you cannot unscramble an egg. This explanation is so widespread that most people accept it and move on. But there is a deep problem with it, a problem that once you see it completely changes how you think about time. The problem is this. The second law of thermodynamics is a statistical law, not a fundamental law. There is nothing in the microscopic laws of physics that forbids entropy from decreasing. If you filmed a glass of water with a drop of ink diffusing through it, ink spreading from a small region into the whole glass, and then played the film backward, you would see ink gathering itself back into a small region out of a uniform mixture. That backward film does not violate any fundamental law of physics. Every single molecule in that film is obeying Newton's laws. Exactly. The time reverse process is microscopically valid. So why does it never happen? The answer is probability. There are vastly more ways for ink to be spread uniformly through water than for it to be concentrated in one region. Astronomically more ways. So the system evolves toward uniformity not because the laws forbid it from doing otherwise, but because uniformity is overwhelmingly more probable. Almost every possible state the system could be in is a high entropy state. But now you should be asking the obvious question. If the laws of physics work equally well forward and backward, and if entropy tends to increase because high entropy states are more numerous, then entropy should tend to increase in both directions in time. If you start from a low entropy state, entropy should increase going forward. But entropy should also have been increasing going backward in time from that low entropy state, meaning it should have been even lower before. This leads us to the question that Ludwig Boltzmann, the physicist who gave us a statistical understanding of entropy in the 1870s, recognized was the real problem. Why was the entropy of the universe so extraordinarily low at the beginning? The second law does not explain the arrow of time. It only transforms the problem. The real question is why we started with such low entropy in the first place. Why did the universe begin in a state of such perfect, improbable order? Before we answer that, let us understand entropy more deeply, because entropy is not just about disorder. It is about information, about the number of microscopic configurations that correspond to a given macroscopic state. The technical term is the number of microstates. When Boltzmann wrote his famous equation, S equals K log W, carved on his tombstone, he was saying that entropy is proportional to the logarithm of the number of microscopic arrangements that produce the same macroscopic appearance. A gas with molecules distributed uniformly throughout a box has astronomically more possible microscopic arrangements than a gas with all molecules in one corner. The entropy of the uniform state is enormously higher. And the second law is simply the statement that systems tend to evolve toward the macroscopic states with the most available microstates because those states are simply the most likely to be reached by random microscopic motion. Now think about what this means for the early universe. The Big Bang produced a universe of extraordinarily low entropy. Not low in the sense that everything was perfectly mixed and uniform. In fact, the early universe was remarkably smooth and uniform. The low entropy came from gravity. Here's something counterintuitive about gravity and entropy. For ordinary matter, a uniform distribution is high entropy. maximum disorder. But for matter interacting through gravity, a uniform distribution is actually low entropy, because gravity can cause matter to clump to form stars and galaxies and black holes. And a universe full of black holes has enormously higher entropy than a smooth, uniform universe. The universe we observe began in a state of extraordinarily low gravitational entropy, smooth, uniform, with gravity's potential to produce structure barely tapped. Over the subsequent 8 billion years, gravity has been doing exactly what the second law predicted, pulling matter together, forming structure, increasing gravitational entropy as stars burn and black holes form, and eventually everything trends toward the maximum entropy state, the heat death of the universe when all temperature differences have been smoothed out and nothing can do work anymore. The arrow of time, the reason your coffee cools and eggs break, is ultimately traceable to the low entropy initial state of the universe at the Big Bang. The physicist Roger Penrose calculated just how improbable that initial state was. The answer is staggering. The probability of a random universe having the low initial entropy we actually observe is roughly 1 in 10 to the power of 10 to the power of 123. That is not a number with meaning in ordinary human terms. It is so small that if you wrote a 0 for every particle in the observable universe, you would not even come close to writing enough zeros. This is what Penrose calls the fine-tuning of the initial state. And it is not a small problem. It is the central mystery of the arrow of time. Why did the universe start in such a profoundly improbable state? Now, there are several attempts to answer this question. Let us go through the most serious ones. The first is the past hypothesis. Philosopher David Albert gave it this name, building on ideas that go back to Richard Feynman and others. The past hypothesis simply states, we postulate that the universe began in an extremely low entropy state, full stop. This might seem like a non-answer. You are simply assuming what you need to explain, but there is something important here. The past hypothesis, combined with the statistical mechanics of entropy increase, successfully derives the entire observed arrow of time. It correctly predicts that we remember the past and not the future. It correctly predicts that causes precede effects. It correctly predicts that we age rather than de-age. All of this follows from the single assumption that the universe began in a low entropy state. The philosopher of physics David Wallace has argued that the past hypothesis deserves to be taken seriously as a fundamental law of nature, not a law of dynamics describing how things evolve, but a boundary condition law describing the state the universe started in. Some laws describe the rules of the game. The past hypothesis describes the starting position. The cosmologist Sean Carroll, however, is not satisfied. He argues that a genuine explanation of the arrow of time must explain why the universe started in a low entropy state, not simply assume it. The past hypothesis is a description. Carroll wants a mechanism. Carroll's own proposal is one of the most ambitious in modern cosmology. He and his collaborators have developed a model in which our universe is not the only one, and in which universes are constantly spawning new universes through quantum fluctuations, a process called eternal inflation on a more general scale. In Carroll's picture, the eternal background of spacetime has no preferred direction of time. It has maximum entropy. And in that eternal high entropy background, random quantum fluctuations occasionally create small, low entropy patches, universes like ours, which then evolve under the second law toward higher entropy, creating an arrow of time in both directions from the moment of creation. On this view, our Big Bang was a random fluctuation in an eternal high entropy background, and the low entropy of our universe's initial state, which seemed impossibly improbable from inside, is just a local statistical fluctuation in an eternal multiverse that has all the time in the world to produce such fluctuations. Literally infinite time. This proposal is elegant and mathematically sophisticated. It is also impossible to test directly for now, which makes it controversial. Now, let us turn to something more concrete. Let us talk about what time actually is in physics, because so far we have been discussing the arrow, the direction of time. But what is time itself? In Newton's universe, time was absolute, universal, a single cosmic clock ticking for everyone everywhere at the same rate. It was the backdrop against which all events unfolded. Time was the independent variable. Everything happened in time. Time happened in nothing. Then came Einstein, and time became something completely different. In special relativity, time is not universal. Different observers moving at different speeds measure different amounts of time between the same pair of events. This is time dilation. A clock moving fast relative to you ticks slower than your clock, not as a mechanical effect, not as an illusion, as a real, genuine difference in how much time passes. More than this, in special relativity, time and space are unified into a single four-dimensional structure called spacetime. What looks like purely spatial distance to one observer looks like a mixture of space and time to a moving observer. The separation between events in spacetime is fixed, but how much of that separation is space and how much is time depends on your motion. And in general relativity, time becomes even stranger. Mass curves spacetime. Near a massive object, time runs slower. A clock at sea level runs slightly slower than a clock on a mountaintop. Your GPS satellites have to correct for this general relativistic time dilation, or they would accumulate errors of kilometers per day. But here is what relativity says about the arrow of time that is most profound. In the four-dimensional space-time of relativity, all moments in time exist equally. The past does not cease to exist when it becomes the past. The future does not fail to exist because it has not yet happened. All events, past, present, future, are equally real features of the four-dimensional space-time block. This is the block universe, or eternalism. The view that all of space-time is equally real and that what we call the present is simply the moment we happen to be at, like a location in space rather than a special privileged moment in time. On this view, there is no objective flow of time. There is no cosmic river carrying us from past to future. There is simply a four-dimensional block in which all events have their fixed positions. Your birth, your present moment, your death, all equally real, all just different positions in space-time. The physicist Hermann Minkowski, who developed the geometric formulation of special relativity, put it starkly. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. It makes the equations of physics clean and consistent. It removes the need for a privileged present moment. But it raises a question that is as deep as any in philosophy. If all moments are equally real, why does it feel like time is flowing? Why does it feel like there is a moving present? Why does the future feel open and the past feel fixed? This is called the phenomenology of time, the way time is experienced from the inside. And it is entirely unexplained by the block universe. The block universe describes the furniture of reality. It says nothing about why one particular slice of that block feels like now. Most physicists who accept the block universe say that the feeling of flowing time is a product of consciousness, of memory, of information processing, of the way our minds encode the past and anticipate the future. The flow of time is real as an experience. It is not real as a feature of the external physical world. This connects the arrow of time to consciousness in a deep and troubling way. The direction of time, the asymmetry between past and future, may be partly or entirely a product of how minds work, of what it means to be a conscious being embedded in a particular region of space-time with memories of some events and not others. Now, let us go deeper. Let us talk about the arrow of time in quantum mechanics, because quantum mechanics brings something new to the table. The Schrödinger equation, which describes how quantum states evolve, is time symmetric. Run it forward or backward, it is equally valid. So quantum mechanics, like classical mechanics, does not contain a fundamental arrow of time in its dynamical equations. But quantum mechanics has a second kind of evolution that is not described by the Schrödinger equation. Measurement. When you measure a quantum system, when it interacts with a measuring device and produces a definite outcome, the quantum state appears to collapse. The superposition resolves to a single definite state. And this process, whatever it is, appears to be irreversible. The collapse of the wave function introduces an apparent arrow of time into quantum mechanics before measurement superposition. After measurement, definite outcome. The process seems to go in one direction only. But here is where it gets complicated. Many physicists do not believe wave function collapse is a real physical process. In the many worlds interpretation, the wave function never collapses. It just branches, with all outcomes occurring in different branches of reality. And the branching process is itself deterministic and time symmetric at the fundamental level. The apparent irreversibility of measurement is, on this view, a product of the structure of the branching, not a fundamental feature of physics. In decoherence theory, which is broadly accepted by most physicists, regardless of their interpretation of quantum mechanics, the apparent collapse is explained by the quantum system becoming entangled with its environment. The environment has enormously many degrees of freedom, and tracking all of them is practically impossible. The information about the superposition is not destroyed. It is dispersed into the environment beyond any practical ability to recover it. Decoherence gives the appearance of collapse and irreversibility without requiring any fundamental time asymmetry. But decoherence, note, relies on the thermodynamic arrow of time. It relies on the environment having low entropy, being far from equilibrium, so that information can be dispersed into it. If the environment were in a maximum entropy state, decoherence would not work as a one-way process. So the quantum arrow of time traces back to the thermodynamic arrow, and the thermodynamic arrow traces back to the low entropy initial condition. We keep coming back to the same question. Why did the universe start with such low entropy? Now let us talk about something remarkable. a genuine physical asymmetry in time that exists at the fundamental particle physics level. I said earlier that the fundamental laws of physics are almost symmetric in time. Almost. There is an exception, and it is a small but important one. In 1964, the physicists James Cronin and Val Fitch discovered that the weak nuclear force violates a symmetry called CP symmetry. CP symmetry is the combination of charge conjugation, swapping particles for antiparticles, and parity, mirroring spatial directions. When CP is violated, then by a deep theorem of quantum field theory called the CPT theorem, time symmetry must also be violated. The CPT theorem says that the combination of charge conjugation, parity, and time reversal must be conserved. So if CP is violated, T, time reversal, must also be violated by the same amount. This T violation has been directly observed. The K Meson and B Meson systems behave slightly differently when time is reversed. The difference is tiny, about 0.1%, but it is real. It means the fundamental laws of physics are not quite time symmetric. There is a small but genuine physical preference for one direction of time over the other, built into the deepest structure of the standard model. But here is the puzzle. This T violation is far too small to explain the macroscopic arrow of time we observe. The thermodynamic arrow, the overwhelming asymmetry between the ordered past and the disordered future, is a vastly larger effect than anything CP violation can produce. CP violation tells us the universe has a slight preference for one direction of time. It does not explain why eggs break and coffee cools. That still comes back to entropy and the initial condition. There is another arrow of time we have not yet mentioned, the cosmological arrow. The universe is expanding. Galaxies are moving apart. The universe was smaller and hotter in the past and will be larger and colder in the future. This gives a direction to cosmic time. Past is the Big Bang. Future is the heat death. But is the cosmological arrow the same as the thermodynamic arrow? Are they the same thing? Or are they independent? Most physicists believe they are related. The expansion of the universe is what creates the conditions for entropy to increase. The universe expanding into a larger and larger available volume gives entropy room to grow. In a static universe, everything would reach equilibrium and entropy would stop increasing. The expansion is what drives the thermodynamic arrow. So the cosmological arrow and the thermodynamic arrow are deeply connected, perhaps identical at a fundamental level, and both trace back to the initial condition of the Big Bang. The expansion began because the universe was created in a very specific low entropy state. Everything flows from that. Now let us talk about something that sounds like science fiction, but is a serious result of taking statistical mechanics seriously. Boltzmann brains. In the 1870s, the physicist Ludwig Boltzmann was wrestling with exactly the problem we have been discussing. Why did the universe start in such a low entropy state? His answer was cosmological. He proposed that the universe as a whole is in a state of equilibrium, maximum entropy. But in such a vast universe, over vast timescales, random fluctuations will occasionally produce low entropy regions. Our visible universe, our observable patch, is one such fluctuation. We find ourselves in it because only in low entropy regions can life and observers exist. This is an early version of anthropic reasoning, and it has a devastating problem. If the universe produces low entropy regions by random fluctuation, then the smallest fluctuation consistent with the existence of an observer is astronomically more likely than a larger one. The smallest possible observer, a single brain, complete with memories of a physical world, floating momentarily in the void before dissolving back into chaos, is vastly more probable than an observer embedded in a vast, consistently low entropy universe like ours. This disembodied brain, fluctuating into existence complete with fake memories, is called a Boltzmann brain. And if Boltzmann's original proposal is correct, we should expect to be Boltzmann brains rather than genuine observers in a genuine physical universe. The fact that we seem to be in a consistent universe with a genuine low entropy past is strong evidence against Boltzmann's original fluctuation proposal. Any successful theory of the arrow of time must avoid the Boltzmann brain problem. It must explain why the entropy of our universe is low in a way that does not generate vastly more disembodied observers than embodied ones. This constraint is taken seriously in modern cosmology. Carroll's proposal and various inflationary cosmology proposals must all pass this test. Now let us turn to the causal arrow of time. We have a strong intuition that causes precede effects, that the present state of the world is determined by the past, not the future. This feels obvious, but it is not a fundamental fact of physics. The equations of physics are time symmetric. They do not single out a causal direction. In statistical mechanics, the reason causes seem to precede effects is the same as the reason entropy increases. Given a low entropy initial condition, the microstate of the universe at any time is much more constrained by what came before than by what comes after. Information flows from past to future because the past is more constrained, more structured, more ordered. Ripples spread outward from the point of impact. A beautiful, expanding pattern of waves. This is the familiar effect following cause. Now ask, why don't you ever see ripples converging on a point and launching a stone into the air? The time reverse process is allowed by the laws of physics, but it would require an extraordinarily coordinated initial condition. Waves on the entire surface of the pond, all curved just right, converging simultaneously on a single point. That requires vastly lower entropy than the scattered, uncorrelated state the pond is normally in. The causal arrow of time, the sense that causes come before effects, is another manifestation of the thermodynamic arrow, another consequence of the low entropy initial condition. The radiative arrow of time is the same. Light spreads outward from sources. Sound spreads outward from speakers. Electromagnetic waves expand. You never see a coherent spherical wave converging on a point, arriving from all directions simultaneously and disappearing into a source. Again, the time reverse process is physically possible. Again, it is astronomically improbable given the actual state of the universe. All the arrows point the same way: thermodynamic, causal, radiative, cosmological, psychological, and they all trace to the same origin: the low entropy initial condition, the past hypothesis, the improbability of the Big Bang. Now let us ask, is there anything at the frontier of physics that changes this picture? One direction is quantum gravity. The problem of time in quantum gravity is severe and deep. In general relativity, time is part of the geometry. It is dynamical, curved by matter, relative to observers. In quantum mechanics, time is an external parameter, a fixed background against which states evolve. These two treatments of time are fundamentally incompatible. When physicists try to write down the Wheeler-DeWitt equation, the quantum gravity analog of the Schrödinger equation, they get an equation with no time in it. The wave function of the universe satisfies an equation in which time does not appear as a variable. This is sometimes called the problem of time in quantum gravity. On this view, time might be an emergent concept, not fundamental to the universe's deepest description, but arising from the structure of entanglement or from the relational properties of subsystems within a timeless whole. Julian Barber has developed this view most fully. In his picture, the universe is a static collection of instants, what he calls nows, with no objective flow between them. The appearance of time flowing is a feature of the correlations between different nows, not a feature of reality at the deepest level. This is a radical idea. It says that time as we experience it, flowing asymmetric with a clear before and after, may not be part of the fundamental structure of reality at all. It may emerge from something more fundamental, just as temperature emerges from the statistical behavior of molecules. Roger Penrose has his own distinctive take. In his conformal cyclic cosmology, CCC, the universe goes through an infinite sequence of eons. Each eon begins with a Big Bang, a smooth, low entropy initial state, and ends with a heat death, a vast, cold, near-empty universe of photons and black holes that have all eventually evaporated. At the end of each eon, Penrose argues the universe becomes conformally equivalent to a new Big Bang, because in the extreme future, dominated by massless radiation, all scales lose meaning, and the universe effectively forgets how big it is. The end of one eon becomes the beginning of the next. In CCC, the low entropy initial condition of our universe is not a random fluctuation. It is the result of the specific dynamics of the previous eon. The arrow of time propagates across eons. The puzzle of the initial condition is deferred, but in a structured, potentially testable way. Penrose and his collaborators claim to have found observational signatures in the cosmic microwave background, concentric rings of slightly different temperature. That might be imprints from black hole collisions in the previous eon. The evidence is disputed, but the proposal is serious. Now, let us think about what all of this means for you, for your experience, for the specific felt sense of time moving forward, of remembering the past and anticipating the future, of having a now. This psychological arrow of time, the asymmetry in your experience of past and future, is real. You have memories of the past. You have no memories of the future. You can affect the future with your actions. You cannot affect the past. You experience the present as a moving now, not as a static location in a four-dimensional block. Neuroscience and cognitive science have a lot to say about the psychological arrow. Memory is a physical process. It involves changes in neural structure, the formation of new synaptic connections. Information about the past is encoded in the structure of your brain. Information about the future is not, because the future is not yet fixed in your brain structure. The asymmetry between memory and anticipation is itself an instance of the thermodynamic arrow. When you decide to do something, You feel that the future is open and the past is closed. The future feels contingent. It depends on what you choose. The past feels necessary. It is what happened, fixed, and unalterable. This asymmetry, the openness of the future versus the closure of the past, is one of the most fundamental features of human experience. But the block universe says this distinction is not built into fundamental reality. The future is no more open than the past. All events, including your future choices, are fixed features of the four-dimensional space-time block. The sense that the future is open is, on this view, an artifact of your epistemic position, of what you know and don't know, not a fact about the world. Whether the block universe is correct, whether the future is genuinely open or merely unknown, this is one of the most fundamental questions in the philosophy of time, and it remains actively debated. Let us now try to bring this all together and be honest about what we know and what we do not. What we know. Time has a direction. The second law of thermodynamics is real and observed. Entropy increases. The universe had extraordinarily low entropy at the Big Bang. The fundamental laws of physics are almost time-symmetric, with a tiny violation in the weak force. The block universe, four-dimensional spacetime, is the best current picture of physical reality. The flow of time is not a feature of the block universe itself. What we don't know, why the universe started in a low entropy state, whether time is fundamental or emergent, whether the flow of time is an illusion or somehow physically real, whether the future is genuinely open or merely unknown, how to reconcile quantum mechanics and general relativity in their treatment of time, what the correct interpretation of quantum mechanics tells us about temporal structure. The problem of time in all its forms remains one of the deepest open questions in physics. It sits at the intersection of thermodynamics, cosmology, quantum mechanics, general relativity, philosophy of mind, and metaphysics. No single discipline owns it. No single answer resolves it. Here is what I find most extraordinary about all of this. We live our lives immersed in time. We cannot imagine existence without it. Every sentence you have ever spoken has been structured by time. Subject, then verb, then object, because then effect, beginning, then middle, then end. Every memory, every plan, every relationship is temporal. Time is the water we swim in. And yet, when we look for time in the equations of fundamental physics, when we ask what time actually is, where its arrow comes from, why it moves in one direction and not the other, we find not simple answers, but a cascade of ever deeper questions. We find that the arrow of time is not built into the fundamental laws, but arises from an initial condition of staggering improbability. We find that time itself may not be fundamental, but may emerge from something more basic. We find that the present moment, the now that feels more real than anything else, may have no counterpart in the external physical world. The physicist Lee Smolin has argued against the mainstream that time is real, fundamentally, irreducibly real, and that the block universe is a mistake. He believes the laws of physics themselves evolve in time, that the past is genuinely fixed, and the future is genuinely open, and that cosmology needs to take the reality of time seriously rather than geometrizing it away. Whether Smolin is right or whether the block universe is right, whether time is fundamental or emergent, real or illusory, singular or plural, remains to be determined. The experiments that might distinguish these possibilities are at or beyond the frontier of what we can currently do. But here's the thing, the question matters. It matters not just as an abstract puzzle for physicists and philosophers. It matters because your experience of time, the moving present, the remembered past, the anticipated future, the sense of temporal flow, is the deepest and most immediate feature of your conscious life. Understanding what time is and why it has the structure it has is part of understanding what it means to be a conscious being embedded in a physical universe. You are right now at a specific location in the four-dimensional space-time block, or you are at a moving now, surfing the wave of becoming at the edge of an open future, or you are experiencing a psychological construction that does not correspond to any objective feature of physical reality. The egg is broken on the floor. The coffee is cold. The past is fixed, and somewhere in the improbable low entropy beginning of everything, in the extraordinarily ordered initial state that the universe somehow found itself in at the Big Bang, is the origin of all of it. The broken eggs, the cold coffee, the direction of your memories. The fact that you are reading this sentence forward and not against all your experience, against all your intuition, in perfect accordance with the fundamental laws of physics, reading it backward.